In this two-part video, I will introduce what's called the wave equation. It's a very important equation in mathematical physics, and it describes the propagation of a wave. So anything like an ocean wave or a wave in a board instrument, sound waves, gravitational waves, which are now a hot topic because gravitational waves were recently detected. All these waves satisfy some version of this. Now, I should emphasize that this is just a one-dimensional wave equation, and that's all we're going to be studying in this course because this is just an introductory course. The true equation is a three-dimensional wave equation. So this describes a wave moving in just one direction. It can either be moving in the positive x direction or the negative x direction. Now, to fully understand this, we need a little bit of understanding of what it means to have this curly sign. This is called the partial derivative, and I'll explain this to you soon. But first, let's make a note of the fact that the function that describes the wave is a function of both space and time. Now, if this were a three-dimensional wave, it would be x, y, z, comma, t. So it would be four variables. Right now, it's just a function of two variables. So even to represent what this looks like is not easy. But let me try doing that. If I plotted y as a function of x and t along the z-axis, and then I had along the x and the y-axis, along the x-axis I'll just have x, along the traditional y-axis I'll have the time t, and along the traditional z-axis I'll have this function y as a function of x and t. So it's going to be a complicated looking object, and I'm not going to make any assumptions about how it looks, but let's just say that it has some three-dimensional shape, something like this. And I'm just drawing a small portion of it. So that would be typically the surface of a ocean, for example. That would be one example of a wave. Of course, I'm doing that surface in only one direction, so it'd be a cut through of that surface, and then as the time evolves, the wave is either going down or building up as time progresses. So don't forget to think of this as a time axis and not a space axis. So what really does the partial derivative mean? Del y by del x and del y by del t. So let's consider. Now, this is not a mathematics lesson. When you actually study multivariable calculus, you'll study these concepts properly. But let's consider a slice at t equals constant. So I'll take some time constant, t naught. That will correspond to taking a photograph of this wave. So let's take a snapshot of that wave. It's going to look like this. The partial derivative with respect to x would be the tangent vector you would get when you find the derivative, which is the slope of this curve at constant time. So this would be the meaning of del y by del x. In other words, the partial derivative is same as the ordinary derivative, except with time kept constant. Now, if you want to have a meaning for del y by del t, you would do the same thing, except keeping x constant. So let's find another curve here, which occurs at some fixed value of x, and that will correspond to maybe looking at a ocean between two tall buildings. So that's approximately keeping your x constant. So you just see the water level rise and fall. That's what's happening here. And so the partial derivative there would just be the tangent to this curve, and that's your del y by del t. In other words, the ordinary derivative with respect to time evaluated at x equals some fixed value. So that's the rough mathematical meaning of the partial derivative. Now, if you take a mathematics course, you'll actually study it in terms of limits and so on, but I'm not worried about that. So as long as you think of it as just an ordinary derivative with the other variable kept constant, you'll be fine. So this has got two of those partial derivatives with respect to time and two of those partial derivatives with respect to space. Now, the other thing I want you to notice about this equation, it's got the right units. If y, let's suppose y has got units of meters, just for the sake of imagining something. So that units of this would be meters per second squared. And the units of speed are just meters per second. So if you do speed squared, you're going to get meters squared per second squared. And then here I have a y, which is meters per meter squared. So you see the meters squared cancel out, and I get meters per second squared equals meters per second squared. So that makes complete sense. Now let's talk about the solutions to this. What kind of functions actually satisfy this wave equation? They're known as the solutions of the wave equation. And they are of two types, and this was first done by the mathematician called D'Alembert long time ago. And he found that there are two kinds of functions which satisfy the wave equation. And these classes of functions can be written as either a function of x plus v times t, or the other kind of function, y of xt equals g of x minus vt. Both of these satisfy the wave equation. Now I just want to quickly show you why at least the first one satisfies the wave equation, and then you can likewise do it for the second one on your own as a little exercise. So let's show that let's show that f of x plus vt satisfies the wave equation. So the 1D wave equation. Let's show that. What I'll do is I'll call this u. So when I do del f, remember I need to show that. So I need to do all these partial derivatives. So it's going to be 4 partial derivatives that I need to do. So del f by del t is the first derivative. I can write that as del f by del u times del u by del t by using the chain rule in partial derivatives. So del f by del u is just whatever it is, and del u by del t, well, that's easy to do. When I differentiate u with respect to time, I just get v. So that's going to be v times del f by del u. Let's take another partial derivative. When I do del 2f by del t squared, well, that's just going to be del by del t of that. So it's just going to be v del by del u times del by del t of f. But del by del t of f I've just worked out here. So I'll just substitute that back. So I'll get v squared del 2f over del u squared. Now I'll play the same game with a space derivative. So del f by del x is going to be del f by del u times del u by del x. And now I look at del u by del x. Well, that's just 1. So that's going to give me 1 times del f by del u. And now for the second derivative, I get del 2f over del x squared. And I just do the exact same thing as I did here. This is just del by del x of del f by del x. But del f by del x is just that. So I'll write it as del f by del u. And then I can take the del by del u on the other side and write this as del f by del x. So by the way, when I do these kinds of things, there are some deep mathematical theorems that allow us to do this, which I'm not even mentioning. And del f by del x from this line is just del f by del u. So that's going to be del 2f by del u squared, the second partial derivative. So comparing this equation, which I'll call Roman 1, and this equation, which is Roman 2, I can see that it immediately satisfies this, because del 2f over del t squared is v squared times del 2f over del u squared, and del 2f over del u squared is precisely del 2f over del x squared. So if you put that there, then I get del 2f over del t squared equals v squared del 2f over del x squared, which is exactly the wave equation here. So that satisfies it, and similarly this satisfies it. Now the waves that satisfy this equation are called forward moving. I'll explain why that is. And the waves that satisfy this are called backward moving. Now that actually is interesting. Why would by the way, I should also tell you that the quantity v here in front of the wave equation, the v is called the speed of the wave. So sometimes it's called the propagation speed. Let's give some examples here. For example, the speed of light. Light has got a propagation speed which is so sacred, it's got its own symbol. It's called c, and that's 3 times 10 to the 8 meters per second. For example, another example, sound in air, which I'll call VSND, is about 343 meters per second. This of course depends on a host of conditions like humidity and temperature and so on, but we just write that. So different waves have different kinds of speed. Light is made up of electromagnetic waves, and sound, which you'll study more in UP2, and sound is made up of just pressure waves, which you'll study later in this week. So that's just called the speed of the wave. Now let's refocus on why the x plus vt solutions are backward moving and the x minus vt solutions are forward moving. Well, that's not very difficult to understand actually. I'm going to think of this f as some random shape. By the way, f and g can be very complicated looking things. I'll give you a couple of examples at the end of the video of what f and or g could look like. But right now, just assume that you can represent f, the shape of f, by this hump. Okay. Typically, when you have a solution like this, it's sometimes called a pulse solution. So let's suppose you have a pulse, and the pulse is we have to figure out if the pulse is moving in the forward direction or backward direction. Let's take this g of x minus vt. Why would this be a forward moving wave? Well, the fact about life that we know is that time always moves in the forward direction. You'll never see time moving backwards except in movies. So if time moves in the forward direction, then this quantity is going to be more and more negative as time progresses. Now, if you want to focus on the top part of this, then the only way to focus on the top part of this is to go to bigger and bigger values of x as time progresses, because this part's getting more and more negative as your watch is ticking, and so you've got to keep shifting to the right to keep this more and bigger so that x minus vt stays the constant. So this g of x minus vt represents a wave pulse that's moving like that. By the exact same reasoning, f of x plus vt represents a pulse that's going in the opposite direction, because as time marches forward, v times t is going to get bigger and bigger, and so for you to keep your eyes fixed on the top of this pulse, you have to keep taking the x to smaller and smaller values, and that means going to the more negative values of x, which means the pulse has to be moving in the backward direction. So the names forward moving and backward moving have to be taken with minus sign for forward moving and plus sign for backward moving. Okay, now I promised to give you an example of what a pulse wave could look like. So here's a wave, and I'm making this up as I'm going. I don't know what's coming through my mind the next minute. So e to the minus u squared sine of tan root u, where u is either x plus vt, or it could also be x minus vt. So this is, believe it or not, something that you can verify satisfies the wave equation. You don't have to do that because I've shown you that any function verifies the wave equation for any arbitrary f. So you can be very crazy about what this function is. What does not verify the wave equation is if you have mixtures. So you cannot have something that's x plus vt on one term and x minus vt. So I'll give you an example of something that's not a wave. So let's look at this. Y of xt equals, I'm running out of ideas, natural logarithm of u cubed, and let's call let's call W x minus Vt, times the hyperbolic sine of u over w. Now that fails to be a wave because I've made this unholy mixture of a forward moving and a backward moving pulse. So those things are not allowed. In part 2, we'll study one specific solution to the wave equation known as the sinusoidal solution. And that's what we'll be focusing on for the rest of this course.